Hi everyone, this is a hands-on tutorial for the mixed formulation for the Poisson problem, and we will navigate into the directory called mixed Poisson in the set of folders for the whole school. And in this mixed Poisson folder, we have just one notebook, so we open it, and here the structure is very much similar to the other notebooks in these hands-on sessions. So it starts with a theory and then goes to examples. And furthermore, I want to mention from the very beginning that this notebook closely follows the lecture on the Poisson problem and on the thermoelasticity. However, we are still presenting here some parts of the theory for you to be able to consult them just in place without looking into the slides. However, if you want to see more details, you're welcome to see the slides provided or the recording of the lecture. We start with this introduction to the mixed formulation, explaining the benefits of the mixed formulation and the reasons for using it, and then also examples which are found in various problems, and then the difference between mixed problems and coupled problems. And then in this tutorial, we're going to look into the Poisson equation. So we start by writing down the strong form of the boundary value problem for the Poisson equation, where we have Dirichlet boundary condition, the zero value of the function u on the whole boundary. So homogeneous Dirichlet boundary condition. And then just for the reference, we state the standard weak form for this problem, where we are searching for a function u in the H1 Sobolev space. So it has the first derivative in the generalized sense. And we're gonna for comparison also solve this this standard weak form. But the real point of this tutorial is to look into the mixed formulation, the mixed weak form. And to get there, we introduce this new variable q for the flux. And now we write the statement or the problem in this way. And therefore, when we multiply the right left-hand sides of the first two equations by the test functions, integrate by parts, we arrive to these integral equations, which will be the basis for the mixed weak form. Once we put in correctly the boundary conditions, as was discussed in detail in the lectures, we arrive to these two equations, and they are the statement of the mixed weak form, where we are searching for a field u in L2 space, in the back space, and in the vector, so the field u is scalar, and the second field that we're searching for is the vectorial field q, which is in the H-div space. And the formal definitions of those these two spaces are given below. So this is the weak formulation, the mixed weak formulation, and we're going to continue by looking into the error estimates. But before that, I want to mention that if you're seeing something like this, that the formulas, the numbering of the formula is not working correctly, please press this button over here. It will recompile LaTeX equations, and it will make sure that the numbering is working correctly, and the hyperlinks are working to the right equations in this document. So we're going to distinguish here between a priori error estimates and a posteriori error indicator error estimates. So a priori error estimates are the ones which are known before we solve the problem. They are the inherent properties of the finite element approximation itself. And here, if we're looking into this a priori error estimates for the mixed problem, and if we ensure that the in-sub stability conditions are fulfilled, and that is being ensured by choosing the right orders for the approximations for the fields. So if we're using approximation order P for the field U, we need to use approximation order P+1 for the field Q. This has also been discussed in more detail in the lecture. So if this is fulfilled, then and then if U star is the exact solution of the problem, then okay, so then the first we're going to write the a priori estimates for the standard weak form, and they are stating that the convergence order is P+1 for the solution U, and the convergence order is order P for the gradient of the solution. Those are very standard estimates that we know for the finite elements. And the norm here is L2 norm in both cases. Yes, and then if you look into the mixed formulation, we get exactly the same properties, that the U is converging to the exact solution with an order p+1, and the Q, which is the variable for the flux, is converging to the gradient of the exact solution with an order p. So what's the main point over here? Well, by considering the global refinement with respect to the element size and with the approximation order of the fields, we can check if our finite element formulation is correct. If we get a finite element solution and we do these checks, we can see if we a priori error estimates are being fulfilled, if we are having these orders of convergence with different values of h and different values of p. But maybe what's more interesting for the purpose of this tutorial is to look into the a posteriori error indicators, because one of the main benefits of the weak formulation is the fact that it provides a simple and easy to implement error indicators like this one, where we would consider the norm of the difference of between the two fields that we find in our problem. So if in a priori error estimates we compare the finite element solution to the exact one, here we are comparing two components found in the finite element solution: the gradient of the field U and the auxiliary variable Q. So we compute the difference between the two, and that would be our error indicator, which will inform us where we should refine adaptively the mesh. And the criterion that we're going to use for choosing the elements where we're going to increase the approximation order is given over here in this last equation. So if for a particular element, we find out that the value of this error indicator computed on this element is greater than the maximum value of all the elements of the error indicator and all the elements in the domain multiplied by some parameter theta, then we're going to refine this element. And what we will ask you to do in this tutorial is to try to change the value of parameter theta between values of 0 and 1 and see how this affects the convergence of this adaptive p-refinement approach to solving this problem. So here are the references used in this part of theory, and we are coming to the part 2 of this tutorial, the example. This is the same example as was used in the lecture. So we're looking into solution of the Poisson problem in 2D domain for a function which is 0 on the boundary, and we construct the solution. And based on that, we find the gradient of this solution and the source term. So we construct a problem, and for which we know the exact solution, and we can check the convergence to this exact solution. Okay, so here the cells for solving the problem are starting. At first, we need a cell to import all the Python modules, parameters, and paths. For the simulation, you will just need to execute the cell once. And after that, if you want, you can hide it, because you wouldn't need to change here anything at all. The second cell is defining some utility functions for generation of the mesh, for running the analysis, and for post-processing. And here as well, you don't need to look into, but if you're interested, you could find some details of how we are using a library gmesh to construct the mesh. That's done over here. So if you're interested, you could look into that. Then you can see how we are executing MoFEM using Python magic, Jupyter magic, to call terminal executable binary MoFEM binaries from terminal, from bash, with the given command line parameters. And finally, if you're interested, you can see how we are using PyVista library to visualize the results in 3D right in the notebook, and in particular how we are using Jupyter backend IPyGNE defined over here, and also panel in some other cases. But This is only what I'm mentioning right now is only if you're interested in these details, in these libraries and how we're using them. But if you're not interested in that, you do not have to look into here. You can just execute the cell by just pressing Shift Enter or by pressing the Run button as anywhere else. And you can as well close it because you wouldn't need to consult this cell later on. But what's actually important and what you can actually try changing are those parameters. So we're going to use an attribute dictionary for storing all the parameters, for pre-processing, for the solution, and for the adaptive refinement, and for the post-processing. And here you can see description of all these parameters used here. Some of them you don't need to change. For example, the side length of the domain is not something you would be interested in changing because we are working here with the predefined exact solution on this given domain. However, element size, the type of the mesh, triangle or quad, this is something you will be able to change. And also for the solution, we're going to differentiate between solution using mixed Poisson formulation and the standard Poisson formulation. You can choose the number of processors to use. Obviously, you might want to use as much as you can, but you cannot use more processors than there are in your underlying system. And also an important parameter is the approximation order. So this number over here, this parameter over here defines this order P, which will be used for the field U. While for the field Q in the mixed formulation, we will be using the order P+1. And there are some additional parameters for tolerance that will be discussed in the end of this tutorial. Okay, so we execute the cell to define the base values of these parameters, and we are coming to the fact that we can now play with the mesh and try to solve something. So we can start with let's probably consider a rather coarse mesh over here, and that's we could choose to use triangles. If you put here the value true, we're going to be using triangles, and if you execute the cell, you will see the output. Yeah, it's a mesh. So if the size is 1 and element size is 0.2, that's what's as expected. We have 5 elements along the sides. And as we chose here true, we have triangles. You will be able to change this later on to see different meshes. And please note that this is all interactive and you can zoom in if you're considering find a mesh and want to see the details. So here we will try to start with the mixed Poisson. We're going to run the analysis. And it takes seconds for this to do the problem. You can see that the error has been outputted and the conversion of results took place. So we can now visualize the results using PyVista that I discussed before. Okay, so for this mesh, the results look ugly because we chose two coarse mesh to represent such a complex solution as given over here with this exponent. So we are looking here at the field U and the field Q, and both of them look weird. So in order to figure out what to do, I suggest to consider a finer mesh with the parameter being 0.05, the element size being 0.05, and you might also want to look into the quad mesh. But I invite you to try to play with other combinations. You can try to different element sizes, and both with the quad and triangle mesh, and see how that affects the results. Yeah, so here now we chose a finer mesh, and we chose to use quads. So now we have 20 quads per each side, so 400 quads in total in this domain. Also, another parameter I invite you to try to play with is the approximation order that we discussed before. So by increasing this, well, you can start from 1 and try increasing this and see how that affects the smoothness of the results that you see over here in visualization. But let's just complete what we've been doing. So the simulation in this final mesh also runs in a second. And if we now visualize, we can see a much better solution. Still not perfect. Still, we can see that there are some probably jumps, tiny jumps, like artifacts of visualization seen over here. So if you want, and if you're interested in this, I invite you to try to consider finer meshes or high approximation orders to get even better results. And I also can see here is the parameter which helps you to choose if you want to use, if you want to see the mesh edges or not. Yeah, so you can, by choosing the value of this parameter, you can decide if you want to see the mesh edges or not. So here, by defining the name of the parameter, we choose which field to show. But for both of these fields, you can choose whichever color map would be suited better to visualize the field in the way that you want to visualize it. Okay, so this was just a preliminary step where we try to generate the mesh, run the analysis, and visualize the results. I invited to play with this part, but I want to continue now to the second part of this tutorial, where we're going to look into the global convergence study. So that's the first step of the convergence study that we're gonna consider, and after that we're gonna compare it with the adaptive refinement. We will see how the convergence takes place when we're looking into the adaptive refinement. But for the moment, we're going to look into the global refinement, meaning that we're going to consider different approximation orders in the whole domain, and we're going to be changing the element size in the whole domain. So here I prepared a few values of these parameters that we're going to try 4 different orders, global orders of approximation P, and we're going to try 4 different meshes with different element size. I invited to try to change these parameters and see other values, but what this cell will do for you is that it's going to try to, for each case of the order, it's going to try all cases of the element size, so 16 simulations in total, as you can see. And for each of those 16 cases, we're going to compute the solution using the mixed formulation and the standard formulation, and we're going to store the results, and we're going to plot them afterwards. So I'm starting the cell, and since there's like 32 simulations needs to run, it's going to take a few minutes, and I will pause the recording and we'll come back when it is ready. So now the simulation in the cell has completed, all 32 of them, and we can now continue to the plotting. So we start with plotting the L2 norm of the finite element solution for both standard and mixed formulations with respect to the decreasing element size. So this is what we are seeing over here. Sorry, and we can use this plot to check the formulation that we are using over here. So we're comparing here the mixed, the full curves with the dashed ones for the standard formulation for the orders from 1 to 4, as was designed, and then the element size is decreasing to 10 to 5 times 10 to power minus 2 to 10 to power minus 3. So we are decreasing the element size 10 times, and we are looking to how the error is decreasing. And hopefully you can see over here that actually the order of convergence is P plus 1 over here, because, for example, for the red lines over here, we are seeing that the error is dropping by 5 orders of magnitude, while the element size is decreasing by 10 times. So this is in agreement with the a priori error estimates for the solution. And now we can look into the a priori error estimates for the gradient of the solution and compare it with what we are seeing in our simulation. So the second plot that we're going to be seeing over here is the H1 semi-norm. So H1 semi-norm is the norm of the gradient of the solution, the L2 norm of the gradient of the solution. And we are comparing it, we are computing the difference between the finite element solution and the exact solution, as is given over here. So we are computing this. And here, in theory, the approximation, the convergence order should be P. And actually, this is what we are seeing on these plots. When again, the element size is dropping 10 times. Over here, when the element size is dropping 10 times, the error is decreasing by 4 orders of magnitude. So the convergence order is 4. And well, another important aspect that we can see in both of these cases is that these results stand both for the standard and for the mixed formulations. they have the same convergence orders. So the theory which was discussed above, the formulation and the a priori error estimates for both the standard and mixed formulations hold. But that's only part of the story, because we want to compare those standard and mixed formulations further. And that's why we are plotting the next cell, which is going to give us the decreasing of the behavior of the L2 norm with increasing number of degrees of freedom. Yeah, because for each of these cases that we studied, each of the simulations that we performed over here in the cell, each of those 16 analyses which were done both for mixed and standard cases, we use different number of degrees of freedom. So we can plot this number of degrees of freedom used, and we can see that the mixed formulation in general is requiring more degrees of freedom than the standard one, which might seem that it's a drawback of the mixed formulation, but the reality here is that we used to get these results, we used global refinement. We decreased the element size everywhere, and we were increasing the approximation or the approximation orders everywhere. That wasn't the case for which actually the mixed formulation was derived and designed in the first place. The real application would be to look into the adaptive refinement, to choose to increase the order of approximation on the elements where the error is high. And before we get to that, before we look into the adaptive refinement, I want to look into a couple of other things. So first of all, the last plot that we're going to plot over here is actually going to compare the error H1 semi-norm. It's the same that we were looking over here. So again, this formula over here for standard, and okay, this formula for the mixed. Actually, we're going to be plotting this one because we're going to be comparing in the next plot the H1 semi-norm of the error for the mixed formulation. So the difference between the field Q and the gradient of the exact solution, and the error indicator computed based on both the gradient of the finite element solution and the finite element vector Q. Yeah, so the H1 semi-norm here is computed based on the difference between the finite element solution for Q and exact solution, and then the error indicator is computed based on two components of the finite element solution: the gradient of the field U and the vectorial field Q. So we're going to compare those two values, and we see that you cannot distinguish between this error H1 semi-norm and error indicator on this plot. They are basically coinciding. So that means that this error indicator is a very good estimation of this error H1 semi-norm. And to prove this further, we're gonna run an analysis on a relatively coarse mesh where we can easily grasp the things by our eyes on the mesh. So we just run it, takes a second, and now by executing these two cells, we're gonna compare visually the element-wise distribution of the error L2 norm and the error indicator. So here on this plot, you can zoom in to see the more details, and you can see that the same elements are being highlighted by the error indicator as the ones which are having high error. But if you press on those three dots over here, you can see the actual values. So you can see that even if the same elements are highlighted, the values of the error indicator are nowhere close to the values of the error L2 norm. They're basically very different. And that's not a surprise, because what's actually coinciding on this plot over here is the error indicator and error H1 semi-norm. So that's what we are plotting in the following two cells. And we're going to be comparing here now error indicator with error H1 semi-norm. Again, the same elements are highlighted. And if you look into the values, we now see that the error indicator is very close to the values of the error H1 semi-norm. So now we can visualize this per each element. We see what's happening at the element level. And we see how close the error indicator is to the real error. And that also explains now why we can distinguish these two in the plots. So I hope this proves that the error indicator is effective and we can use it for adaptive refinement. So this is what we are going to do in this last exercise in this notebook. So we will look into adaptive refinement. So we're going to use a couple of parameters which are needed for the for this adaptive refinement. So we need to choose the value of the tolerance of this integral value of error indicator to know when to stop. And also we need to choose this parameter theta. I remind you to look into the theory above to consult this formula over here to see how the parameter theta affects the choice of the elements where the approximation order will be increased. So this is what's going to be done over here. So we start with the value of the parameter 0.5, but like I was saying in the beginning of this recording, is that you would be asked to change this parameter to see how this affects the results. Other than that, all other parameters are being set as before. We are maybe only one change here is that we're going to start with order 1, because we're going to be progressively increasing the orders of the elements which needs this order refinement. And then we're going to go to very high orders. I invite you to see how this was showcased in the lecture. But here, the simulation which has been triggered over here is basically taking also seconds. Okay. It's still running, going through those cases, and it's done. And so the next cell is plotting the results of the simulation, which was done over here. And it's different from the previous studies, as it didn't run several times. Well, I mean, the MoFEM was executed only once, but the solution was obtained inside of it several times with those iterations of the refinement. So we started with the case when there was order 1 everywhere. Then we chose the elements to be refined according to the formula, and then according to the criteria discussed above. And then we increased the order of those elements, solved again and again. It was all triggered by this function over here. And as a result, we can now compare this global refinement, the standard finite element formulation, with orders 1, 2, 3, and 4, with this adaptive p-refinement used with the mixed formulation. And we can see now the benefit of the mixed formulation, but that by using this adaptive refinement, only by increasing the order and the elements where the error is high, we could obtain the solution with the same H1 semi-norm, the same error, with 20 times less degrees of freedom. So this was the whole goal of implementing the mixed finite element formulation for this problem. The only thing that I invite you to try to change over here is this parameter theta, because you can see that we did get below this threshold of 10 to the power minus n for the error semi-norm, H1 semi-norm, but we had to do quite a lot of steps. So each circle on this plot corresponds to the step of the solution iteration when we refined. So I invite you to change the parameter theta and rerun the cell and rerun this plotting over here to see if you can get below this tolerance, this 10 to the power minus n tolerance, with a less number of refinement iterations, and if possible, with an even less number of degrees of freedom. Yeah, so you would just change this parameter over here to something else, like for example 0.2, or on a different side to something higher, to 0.8, rerun this cell, and rerun this cell to plot the results. That's all what I wanted to show over here. Thank you for your attention, and let us know if you have any questions. Bye.